11.7, the whole goal is here we're going to be finding maximum and minimums. And as always, you're going to be finding critical values first. And of course, what is a critical value? Okay, well, back in the time, it was you find f prime of x, you set it equal to 0. So let's say at x equals a. In other words, what you'd be saying is this: f prime of a rather, would give you a 0. And then you could do a couple of things. You could look at it in terms of, well, okay, so this is where we have a tangent line of 0. So then the question is it a situation where the first derivative on this side was positive and now it's negative, ergo that would be a maximum. So f prime of x is positive when x is less than a, that is, this is x equal a right here. Well, and f prime is negative x greater than a. That's the first derivative test, and that would give you a maximum. Of course, if you had it the other way around, f prime of x less than 0, when x less than a, then you'd have a situation kind of like this, so it's decreasing, and then it begins to increase at x greater than a. This would be a minimum. So that's one way to do it, and that's the first derivative test. Now, if you recall the second derivative test, and the idea with second derivative was you take the second derivative, so f double prime at a, right, because that was our critical value, and you say, well, what happens? Well, of course, if f double prime at a is positive, that would suggest that we have this situation, that is, it's concave up, which would give us a minimum. Or, of course, if f double prime of a is negative, then it would be concave down, which is this scenario, and we would have ourselves a maximum. Well, 2 dimensions, or 3 dimensions rather, it's going to work somewhat the same. So instead of doing f prime equals 0, you're going to do f sub x rather, the first partial with respect to x equals 0, and this fella equals 0. That is, you need an x and y where these are both true at the same time. Right? This point xy right there, that guy is your critical value. There might be more than one. Now, in 3 dimensions like this, we only use what's called the second derivative test. It's the only real easy, nice way to do it. In second derivative test, it goes down like this. You make yourself what is called a don't make yourself what it's called a. You're making a determinant, and in the determinant, you're going to have these fellas. So that's your determinant, which of course, as you know, is fxx times fyy minus this guy squared. And so what you're going to do is you're going to take this thing here. This is your test value, and the book, of course, refers to it as something, and they call it D for determinant. It's kind of cute, right? And so they give you a few ideas. They say if, okay, and here they are. And it says this: if D is greater than 0, and fxx is positive, then you have a minimum. Okay, now this is very similar to what happened before. That is, this is the second derivative just in the x direction. And again, if it's concave up, then it's a minimum. But only if this is true. Because what happens when you're doing this is this. When this thing comes out to be greater than 0, then that means it's either going to be a maximum or a minimum. The question then will be related to, well, what happens to this portion of it. Now there's a part 2. Well, what happens if it's this and this is this? Well, it's a maximum. And then, of course, if this is a whole different kettle of fish. If this is less than this, then it is not a local max or min. Most of the time it's a saddle point, but there's a couple weird exceptions when it's not. So we'll talk through that situation. So as I mentioned earlier in one of the other videos, a saddle point can be viewed as both a maximum and a minimum. So kind of like driving over the top of a pass. You're coming up the highway like this, wee up and over the top. Like, yeah, reach the top of the pass, and then you shoot through. It's called a pass because it goes through the mountains. It is not the highest point in the neighborhood. In fact, it could also be considered one of the lowest points in the neighborhood. So it's both a maximum and a minimum at the same time. It's a saddle point. And if you picture, here it is Roy Rogers here straddling his saddle. That's why they call it a saddle point. Okay? And so the idea being is here is whenever you have a saddle point, it's, well, first of all, any saddle point, well, this was what you'll end up with. But not 100% of the time does when this determinant is less than 0. It doesn't always mean it's a saddle point. But a saddle point will always be less than 0. So it's not an either or. It's not a if and only if scenario. So here's how this thing's going to go down. Now there's a few definitions we'll look at a little bit later in terms of just defining it and making it a little bit tighter. But that's the game, and I want to run through a few here and see how we feel about them. Now you'll notice what I'm doing here is I'm making up a function such that I have a pretty good idea what this function looks like. And so I think a person should always, anyway, as I was saying, I think a person should always graph these functions to start with. So you get a pretty good idea what's going on. Okay? You still need to always do the actual math, but I think it's helpful and instructive to know if your math even makes sense what you're doing. So x squared plus, what did I say? No, it's 3x squared plus y squared. Isn't that it? Dang it, I'm doing everything wrong today. Okay, and just as I suspected, since x squared and y squared were both positive, I suspected it would look something like this. And by the way, I also know that from earlier chapters we've talked about, well, suppose you do the traces of this thing. Well, if you let y be a constant, you get x squared, which opens up. And if you let x be a constant, then it's y squared, which also opens up. So I had a pretty good idea that this thing was a minimum value. Okay, so I know that going in, I feel pretty good about it. So I know what I'm looking for, which is nice, and so I kind of make sure that points me in the right direction. So if I do this, like the partial with respect to x, I get 6x plus 2y. And if I take the partial with respect to y, I get 2y plus 2x. Now, this one isn't that hard to do, but some of them later on will get ugly, so, or it could get ugly. So I'm going to show you how to do it the easy way on a calculator in terms of solving that. Now, of course, you could always, do it old school. I mean, you all took Algebra 2 at some point or something, and so you could, if you wanted to, solve for x and y such that it's 0, 0. And it turns out it is 0, 0. But I'm going to show you what I would do on my calculator if I ran into one that was a little uglier than this. So a little F2 solve, and the functions are 6x plus 2y. Y equals 0. Second, 5, 8, 8. So and 2y plus 2x equals 0, comma, squiggly brackets, x, comma, y, squiggly parentheses, bam. And you'll see that it's 0, 0, which makes perfect sense because that's about the only one that could happen to. So 0, 0 is our critical point. Okay? Now, to set up the determinant, okay, we need the second partial. So here's the first partial. So we need to take the derivative of this again with respect to x, which gives us, of course, a 6. I'm going to take the derivative of this guy with respect to y. Now that's a 2. And then if you recall from the other night, the mixed partial says you can either take the first derivative with respect to x and then do it with respect to y, or if you prefer, you can do it this way. So it doesn't matter. So if I take this fella, I've already taken the derivative with respect to x, so now I derivate with respect to y, gives me a 2 and a 2. So then d is equal to 12 minus 4, which is 8. So over here, if d is positive, so check, it is, and if this guy is positive, which it is, check. Oops, where'd it go? Therefore, we would have a minimum value. So what we're saying here is this. We're saying that 0, 0, 0, 0 represents a minimum. Now, I don't want to bore you to tears with the details because you know this. You know, for instance, that this guy right here is a local maximum. He is also a local maximum. And this function has no overall or absolute maximum because it goes up forever. Oh wait, now it does. That's the global or the absolute maximum, but these guys are still relative, yes? And so the idea that your book points out is the idea of a local max or a local min. It just means in the neighborhood. And so what they say is this: in a disk, it is the largest in the case of a maximum, or the smallest in the case of a minimum value in the neighborhood. Dadgummit. Okay, let me pause for a minute. Crap. Alright, so it's the largest or smallest in the neighborhood. This is the highest point in this neighborhood, say, from here to here. Well, in the xy situation, if I look at x and y, picture it as this is the highest z value, some z value that is the biggest, the big Z. It is the biggest in some neighborhood. Okay, and that neighborhood will be bounded by some sort of a disk. So instead of bounding it by some little, like from A to B and saying that's the highest y value in this neighborhood along the x-axis, we're going to say this is the biggest z in some circular path or some disk around it in that neighborhood. Okay? It clearly does not mean it's the highest point. It just means it's the highest point in the neighborhood. Okay? Now I'm going to make this next problem a little nastier. Not much nastier, so don't freak out or anything, but a little bit nastier. And so, for instance, maybe it's 3x cubed y plus 2xy minus 3x squared y squared plus 5. Alright, again, not very difficult. Simply take the derivatives. So with respect to x, it's 9x squared y. God dang it. Plus 2y minus 6xy. Worthless pen. Y squared. What's wrong with you? Seriously. Oh, brother. And f sub y, then, we would say is, so it's going to be 3x cubed plus 2x minus 6 x squared y, and that should do it. And we set both of them equal to 0. Now imagine back in the day trying to solve these dudes. Now it's doable and it's not horrible. For instance, this top one, if you're a glutton for punishment, you know who you are, little masochistic tendencies perhaps. A person could factor a y out, for instance, and you'd get 9x squared plus 2 Alright then. So I factor an x and a y out of each of them. So obviously 0, 0 makes it possible. These also may have solutions, right? So I don't know. Point is I can take my calculator and I can solve these guys. Now this is probably the messiest one that you will see. Right? It's just, it isn't that horrible. So I'm going to use the calculator to solve. I'm going to solve. And remember, when you're doing them this way, you must 9x squared times y plus 2y minus 6x times y squared equals 0. And 3x cubed plus 2x minus 6x squared times y equals 0, comma, squiggly brackets, x, comma, y. Now some of you might be wondering why I didn't graph it first this time, because, I don't know, I wasn't paying attention, I don't know. So I graph it, and I think I solve this, and I see that, oh, in fact, it's only 0, 0. So that kind of makes me think, well, let's go graph the dumb thing. So now there's nothing wrong with doing it the way I did it, like in terms of, I chose to not graph it first this time. X cubed y. Ordinarily I would, for whatever reason I didn't this time. Plus 2xy minus 3x squared y squared and there it is. Okay, and so this isn't going out very far, and so I'm going to go ahead and adjust this like negative 10, and negative 10, oops, 10, and negative 10, 10, and oh hey, that's pretty cool. So when I do this, I see that, oh weird, check it out, check it out. The only place I see a point, I see this whole kind of a ridge along here, but a ridge isn't defined as a maximum point. And the same thing going the other direction, I see some ridges. But what I don't see, the only point I see is that point right there. And if you look at it, it sure looks like it ought to be a saddle point. Okay? So in a minute, what we're probably going to see is at the saddle point. Now, it's maybe such that if I zoom in, I'll see that it doesn't exactly look like a saddle point, but from this vantage point, it sure does. Now, another way to tell is to look at the contour plot. So if you look at that contour plot, ooh, that's kind of bad. And if you come in here to the contour plot and you change it, and so you start at, say, -1, let's count by 1 this time, just for fun. What you see is this classic, absolute classic look. That is, when you see it, you see to yourself, well, it seems to be increasing coming this way and, say, decreasing coming across this way. When you see that look, that's pretty typical of a saddle point. Okay, but we'll see that in a minute. Maybe one that's a little better when we look at it. So back to the graph we go. Okay, so 0, 0 is our critical value. 0, 0 is our critical value, so that's where we're starting from. So we make our determinant now. And our determinant is the second derivative of this guy with respect to x. So 18x. And then over here, the derivative with respect to x gives me minus 6y squared. So minus 6y squared. I'm going to fatten this up a little bit. There we go. Now, the second derivative of this with respect to y would be negative 6x squared. And then if I take the derivative of this with respect to x, I get what? 9x squared plus 2 minus 12xy. And of course the same thing happens down here. 3x cubed plus 12x minus 6x squared y. And now, what value are we plugging in? Well, we're plugging in our value of 0 and 0. So this is an interesting one. We get 0, 0, 0, 0. And so we get this. We get, well, our d is equal to 0. Well, that's weird, because Jay, you didn't mention that to us. Well, yeah, there's a few bizarre points. It says if d equals 0, the test gives us no information. Well, now why is that, do you suppose? Okay, well, let's go back and look at the graph again. So let's look at the actual graph and look at it like this. Notice how that line comes straight down the axis there. I wonder why that is. Interestingly enough, when I approach it down the x-axis, things change. But when I approach 0 down the y-axis, nothing changes. Well, if you come back into here, what you'll see is this. The original function, okay, everybody's got a y in it. So if y equals 0 on every single one of these, as long as you're along the x-axis where y equals 0, this is going to be 5 always. So what you're seeing is this. Here's the x-axis, aka y equals 0. And here is the point 0, 0. Ah, dang it. 0, 0. Okay, there's that point. Now, as you approach it from this direction, anywhere along here, the z is equal to 5. That is, it's neither increasing nor decreasing. And the same thing is true coming from this direction. So it clearly can't be a maximum because it's not changing. It clearly can't be a minimum because it's not changing. It can't even be a freaking saddle point because coming down this way, if you flip it around, we look at it this way. Oops, sorry about that. We look at it this way. If this is the y-axis, okay, aka x equals 0, okay, well, coming back at the graph, what do you see? Stop moving. Stop it. You see it coming downhill as you come and approach it. It's coming down as you approach 0. And if you look at it, it makes perfect sense, coming back to the original function. As x's are approaching 0, as you approach 0, 0, 0, what you end up with is, okay, let this be something other than 0, okay, as you do that, these things, this whole value is approaching 5. It's decreasing to 5. And so, the reason this test gives us no information, because as you approach 0, 0 here, this one comes down. Like as if it were going to be a minimum. But this one is neither decreasing with it nor increasing to it. It's not doing anything. So because it's not doing anything, it's neither a saddle point nor a maximum nor a minimum. In other words, it is the idea that you're tracing along a ridge, you know, between two peaks like this. It doesn't have a name, so we just say this doesn't tell us any information about it. Now, let's do the one that I did for my, if you've already watched the sample tonight of the contour plot example, I used this fella, 0.1 x squared plus 0.4 y squared plus xy. Okay, so we know that. We already know that this is 0.2x plus y, and this is, f sub y is equal to 0.8y plus x. And again, set them both equal to 0. It's pretty obvious to see that in fact it's going to be 0, 0 for both of them. But if you can't see that, go ahead and use solve. But there's our critical value. So if we're going to set up our determinant, the second derivative here is 0.2. Second derivative here is 0.8. The derivative of this dude with respect to y rather is 1. And so what you end up with is 0.16 minus 1, which is equal to, and gummit, negative 0.84. Okay? Now, because the d is less than 0, it is neither max nor min. And as I say, 99% of the time, you will find it to be a saddle point. Well, that picture that I drew earlier, and I'll go ahead and regraph it real quick so we can see it again, is that classic saddle point look. And that is that classic saddle point look. And where does it occur? It occurs at 0. That's the look of the graph, and here's its contour plot. And it goes like that. And as you can see, as you're coming up this direction, oops, I'm sorry, you can't see what I'm pointing at. As they're coming up this direction, they are increasing. They are increasing. That's not exactly what I wanted. Stop it. They're increasing. They reach a maximum, and then they peter off down to the side. They are decreasing to a minimum, and then they come up the other side. And that x, crisscross x look that we see right here, that is classically indicative of a saddle point. Alright. Here's one right off the homework page. Let's do this one. Let's do y squared minus 2y cosine x. And this, of course, is f of x and y. And notice this time we're going to be on an interval from -1 to 7. Now, why is that important? Because this thing will keep doing its thing forever, right? And so you need to pinch it off in some sort of space. So let's look at this. If we do this guy, we're going to find our critical values first. So the derivative with respect to x is simply going to give us positive 2y sine x. And f sub y would give us 2y minus 2 cosine x equals 0, equals 0. Make sure that you are in radians when you pull this off. My stupid calculator is having an issue. Every time I turn this dumb thing off, it changes back to degrees for some unknown reason. But I'm going to fix it. Okay, now, so F2, we're going to solve 2y times sine x equal 0 and 2y minus 2 cosine x equal 0, comma. Okay, and so x is at pi times constant. So in other words, x is equal to n pi, and y is equal to y equals cosine of pi n. Oops, what are you doing? Y equals cosine of pi times n. Okay. Or, what else does it say? X equals pi over, that's what this is saying to us is this: if you distribute that out, pi over 2 times 2 is pi. So it's pi. So it's pi here minus it's pi n minus pi over 2. Okay. And what's the other one? And y equals, if you trail it over a ways, y equals 0. Okay. Now let's think about why that's true. Alright, so if that's true, then the cosine of pi times n, okay, well, why would that make it 0? Well, if you come up here and look at this value here, okay, the sine of pi, any multiple of pi, right, is going to cause this to be 0. So that part will go away. So that makes that part true. And then down here, the cosine of pi is as you know, 1, so that's negative 2. And then you need 2 times y. And so if y is this, then it becomes exactly the same function as this. So I'm sorry, this goes into here, this goes into here. That would also make it true. Okay, so, or you could do it this way. So pi, so if it was 0, that would be negative pi over 2. Negative pi over 2 is negative 1.57, so that doesn't make any sense to us. Okay? So if I start with n equals 0, then this becomes negative pi over 2, which is negative 1.57. So that's no good. If I make n equal 1, then this becomes pi over 2, so that becomes positive 1.57. Plus pi would be, as you can see, something like 4.6, right? Right? Add 3.14 to that, thereabouts. And if you add pi to that again, where do you end up? You end up at 7.7. So that's no good, yes? So we're looking at these two guys right here. And what would the y values be? They would be 0 and 0. Okay? Now, I'm going to graph this in the 3D calc plotter and see what I like about it. So it's y squared minus 2y times cosine of x. Like that. And I'm going to change, before I get started, I'm going to change my values to, excuse me. Now, it's strictly restricted our x values, so the y's can do whatever, kind of whatever they want, but I'm going to go ahead and restrict these to negative 1 to 7. Now notice that's a distance of 8. So I'd kind of like these ones to match up with it. And so I'm just going to go from like negative 4 to 4, and I'm going to see what that does for me. And I think I'm going to do this one negative 4 to 4 as well. Now, right now I'm keeping them so that they're the same, so that it makes it a nicer box that way. And it may or may not work well when I get my stuff in. Oh, I didn't ever hit graph, did I? Oh, there it is. Cool. And as you can see, when turned on its side, it sure looks like I ought to have how many values? It sure looks like I ought to have 3. Okay? And so if you look at it, you're like, well, okay, yeah, I can buy that this one right here is maybe a value that makes sense to me. These two both look like they're on the y-axis, so 0 is my y, And so I think I can bank on that this one is somewhere around pi over 2, right? Maybe able to sell myself on a couple of these points as being points that I'm happy with. And we'll kind of play it by ear. So that's what we're going to go with. So it looks like I have 3 values here that are obviously what? This is obviously a minimum, minimum, minimum. Spin it around. Well, wait a minute though, because that kind of feels like we have a what in there? Well, we have something going on right there. So I have this kind of a feeling and that kind of a feeling. So at that point right there, do I have some sort of a maximum in there? Sure looks like it might be a maximum. So how am I going to find all the rest of those values? Okay, we're going to talk about that in just a second. While I have this picture up, I'm going to hit contour plot so you can see what that baby looks like. And I'm going to make them go by 0.2s or something again. And as you can see, what I've got here, those are saddle points. That's classic saddle point here and here. So what does that tell me? Well, that's about 1.57 comma 0. So that's that point we just talked about. So that guy looks like a saddle point. This is that other saddle point, or the other point, 4.6 comma 0. So that's our other saddle point. And then we've got these guys. And you're like, well, what are they? Well, notice how the inner ring is a bigger negative here. So that means this one happens to be a minimum. This one over here looks like our height. That looks like it to be a maximum. Looks like to be anyway. And then this one here, I can't really tell, so I have to follow some lines around. I don't see any good data for this one, but we'll play it by ear and see what we get. Now, back over here then, how do we find these guys? Okay, so if you let x equal what? If you let x equal, well, let's start off with 0, right? Or n rather. So let's let, so we got these two values. Then I can let n equal 0 here, so that would make x equal 0. And what happens when you take the cosine of 0? You get 1, right? And, well, what happens when you put a 1 in here? You're going to get pi, and you're going to get what? Cosine of pi is negative 1, right? And then if you let n equal 2, you get 2 pi, and you get the cosine of 2 pi, which is 1 again. So these look to be our 5 values. So now it's just simply a matter of, we kind of see from the picture what we thought they ought to be. Maybe. We kind of see the general description. These two have to be saddle points. I mean, that's just obvious. But let's look at our d value here, our determinant. So if you take the derivative of this with respect to x, you get 2y cosine x. Okay? If you take the derivative of this with respect to y, you get 2 sine x. You also get that down here. And if you take the derivative of this guy with respect to y, you simply get a 2. So cross multiply, you get 4y cosine x minus 4 sine squared x. And so now it's simply a matter of plugging in values. So if you plug in, and again this is pi over 2, and this is technically 3 pi over 2, I believe, you will find. And that's pi over 2. So the cosine of pi over 2 is 0, so that's cool. And the sine of pi over 2 is 1, so minus 4 then, so negative 4. So for pi over 2, comma 0, we get that d is less than 0, and we've already seen from the picture that means this guy is a saddle. Let's try 3 pi over 2. So again, you plug it in. The cosine of 3 pi over 2 is also 0. The sine of 3 pi over 2 is negative 1, but you square it's positive 1. It's the same exact value then. It's also, so this is also a saddle. Okay. Now let's stick one of these dudes in. So for 0, 1, you plug it in. Well, if x is 0, the cosine of 0 is 1, times 1 is 1, times that is 4. The sign of 0 is 0, so that's positive. Okay? And notice that when you put in this value into here, if you put 0, 1 into this guy, you get 0 here gives you a 1, and a 2, so it becomes a 2. So D is positive, and F double prime of X, like this, is also positive. Hence, this is a minimum. Okay? Let's try pi and negative 1. So if you take the cosine of pi, that's negative 1. Times negative 1 is positive, times that, so that's 4. Hey, the sine of pi is 0, so that's cool. So this is also positive. And again, if you put pi and negative 1 into this dude, you get positive 2. So once again, this dude is positive. Hence, this is also a minimum. Okay? So you plug 2 pi in. Cosine of 2 pi is 1. Times 1 is 4. It's 4. Sine of 2 pi is also 0. So this again is greater than 0. Ah, you hippie. That's greater than 0. And it's just 2 pi, comma 1. And if you come over here, you're like, okay, so cosine 2 pi is 1 times 1. Yeah, it's also positive. Hence, these guys are all minimum. Okay, and again, that is what the picture seemed to show to us over here. Let me just regraph the dumb thing. There it is. And again, turned on its side. Looks like I have 1, 2, 3 minimums and 2 saddle points. And if you stop and look at it, this is y equals 1 along this line here. If you spin it around, that sure looks an awful lot like 2 pi right there, and that sure looks an awful lot like pi over 2 over here. Or, sorry, 0 over there. And then this is pi, and that is negative 1 right there. Okay. I think that's probably enough of those. I think it's just a matter of once you see the gist of it, it's pretty easy to do. I think there was one last thing that I wanted to talk about, and that is just the extreme value theorem in 3 dimensions. I just wanted to just throw it up here so you can go, oh yeah, he told us about that. That's neat. It's not very difficult though. So, the extreme value theorem, if you recall, back in the day, you talked about it in 2 dimensions, not 3. And the extreme value theorem just says this. Your extreme values will occur where? Your extreme values on an interval, an interval on an interval. Wow, I really need to get this board fixed. I'm going to pause you. Alright, so in 2 dimensions it looked like this. So, for instance, if I had, good grief, I hope this is just a battery going dead thing. This is really getting on my nerves. So if I had a function that looked like this, and I said, hey, look, on the interval from here to here, the function just keeps going up, I guess. There we go. Cool. Where does the maximum minimums occur? Well, there is one critical value in this interval. So this is where either a max or min lies. It's obvious from looking at this as a minimum on that interval. And the maximum will either then occur at this endpoint or this endpoint. And it's pretty obvious that this one is the bigger one. So that's what it looked like in 2 dimensions. In 3 dimensions, it's a little bit different. It says this: if f is continuous, so every function we've looked at tonight has been continuous in the area in question. Okay? It just says on a closed, bounded set in R2. In other words, I could say, hey, look for it in 2 to 3 by 1 to 9. These are my x's, these are my y's. Almost like a window, if you will. So as long as your function is continuous everywhere in here. Now, it could drop off the planet over here at x equals -7. But in this interval, from x goes from here to here and y goes from here to here, the function is continuous on this interval. Then here it is. Then f attains f, which of course means z, right? Right? AKA. Then your function attains an absolute maximum f of x1, y1 and an absolute minimum f of x2, y2, right? At some points x1, y1 x2, y2 in D. And again, this thing right here is my D. That is, this from x goes from here to here, and say like y goes from here to here. Okay, now that's in essence what we said before. Okay, so if there's a critical value in here, okay, and that critical value is a maximum or a minimum, then then these extreme values will occur at those points. If there aren't any places where, for instance, first of all, we have to see this equals 0 and this equals 0, right? So if there isn't a critical value, excuse me, in this region, okay, then obviously that part of the thing doesn't exist. In other words, there doesn't have to be a full-on, there it is, it's obviously a minimum. It's great, it's perfect. It doesn't have to happen that way. For instance, you could have a plane cutting through here like this. You know, this plane that goes out that way forever. Okay? Does it have a minimum value on this interval? Yeah. Does it have a maximum value on this interval? Mm-hmm. Does it have any place where the slopes are 0? No. Okay? And that is literally as hard as it gets. Okay? Not a very hard concept. We will be doing some more of these. You know, if you graphed things like you've always expected, negative x squared minus y squared plus 2. X squared plus 2, negative x squared plus 2, you know what that looks like. And oh, by the way, negative y squared plus 2, you also know what that looks like, right? So are you going to be shocked when this looks like a paraboloid that opens down where there's a maximum right there? Well, I'm not shocked by that at all. There'll be some times when you will be shocked. You'll graph it and you're like, whoa, I had no idea what that looked like. But when you graph it, you will see that it has minimums or what looks to be maximums or what looks to be saddle points. And don't be shocked if you see like 6 of those. Well, then you better have 6 critical values. If you see 6 minimums, no maximums, and 2 saddle points, then you better have 8 critical values. Okay, just know that going in. If you don't, you probably screwed up somewhere. All right.